And this is Naiqian Zheng from Peking University. Today, I'm really glad to share our work about service mesh testing. It is a joint work with Tianshuo and my advisors, Xuanzhe and Zheng. Recent years, more and more cloud applications are designed loose-coupled. They divide themselves into microservices and communicate via RPC. However, the shortcoming is that each microservice has to develop and maintain its own RPC communication logics, which brings heavy burden to the developers. So to solve this problem, people choose to use service mesh to take over the RPC communication among the microservices. Developers only need to define the network functions on service mesh, and after that, the service mesh does everything else. With service mesh, we have a lot of benefits, including less maintenance cost, better reliance, and better observability. So actually, service mesh is the narrowest for microservice communication. And it's very popular on GitHub, widely used by industry, and has already been integrated in modern clouds. Service mesh provides rich functionalities, including traffic management, authentication, security, and observability. And among them, service traffic management is the fundamental one, because it decides where to transmit the service request and how to rewrite it. So it is also the focus of our work. The rich functionalities always brings complexity. The input of the service mesh is communication configuration, which includes tens of CRDs and millions of options. And the output of service mesh is some abstract network behaviors. And it's very complex because it needs to handle any type of request in the network. Thus, the code base of the service mesh system is extremely complex. For example, Istio has more than 1,000 components and over 300,000 lines of code. But unluckily, complexity always brings bugs. Here, we show a real bug from Istio on the left. It is found by our work. The bug happens when two service entries have the same host and different port. It makes one of the service entry does not take effect, and finally lead to a service unavailable error. The root cause is the incorrect rule merging in the code base for EDS. It's not covered by existing tests because the developers didn't think of this rule merging situation. We found this bug, reported to the developers, and finally they have fixed it. An important reason for the vulnerabilities is the insufficient testing. We found that the majority of existing tests are unit tests. For example, Istio has more than 10,000 unit tests. But however, they have very few end-to-end tests. Istio and Linkerd, the two most famous service mesh systems, only have 160 and 30 end-to-end tests. The lack of end-to-end tests makes the service mesh not reliable enough, especially in the interactions between network functions. The bug mentioned before is very simple for end-to-end testing, but difficult for unit tests to cover, because it is caused by the interactions between functions. So let's do some end-to-end testing. We know that the input is some configurations on the network functions, and the output is the network behavior. Thus, the testing has to be in two steps. And on the first step, we should generate various service mesh configurations. And the second step, we should check whether service mesh realizes the input configuration correctly. However, creating input configurations is very challenging. This is because that the configurations must be end-to-end effective. Here we define an input configuration is end-to-end effective if the configuration is able to take over and route the request to the destination, like the green lines on the left figure. If all the lines are broken in some stages, such as the red lines, the request cannot go to the destination, so the input configuration is not end-to-end effective. To do so, the resources must cooperate to connect to each other from the source to the destination service. As a result, it will compose end-to-end service flow paths from the entry to the exit. Besides, it should also pass validation rules for each function to make sure the service mesh can accept it. We all know that symbolic execution and fuzzing are some common practice for generating test cases, but they cannot be directly applied to service mesh systems. This is because symbolic execution always explodes in the options, and the fuzzing is very difficult to compose end-to-end service flow paths and not easy to pass validation. The second challenge is correctness checking. The output of service mesh is some abstract network behaviors, which cannot be directly checked. What we can do is to check whether one request is handled correctly or not. But the correctness of the holistic network behavior requires the system to process any request correctly. So we need to choose a finite and comprehensive set of requests, which is representative for all the requests. After that, we need to infer correct processing behaviors of each representative request. So most importantly, the checker should be automatic, since it needs to check a lot of test inputs. Actually, to solve these challenges, we present MeshTest, an automatic end-to-end tester for service mesh systems. The input of MeshTest is in gray, including the resource definition, resource connection definition, and the CFG interpreter. It works automatically to produce test results. It consists of an end-to-end configuration generator and an automatic service mesh oracle checker. The input generator is to create various service mesh configurations as the test inputs, and the testing oracle is to check whether the system can handle the input configurations right. Certainly, the input generator and the testing oracle work together in MeshTest, but they can also work separately to be integrated in other tools. More specifically, MeshTest has 4 stages. I will introduce them one by one. First, we start from the service flows, the key of end-to-end testing the input configurations. Service flows depict how requests are handed over between resources and finally routed to the destination. We use a domain-specific service flow skeleton model for modeling the service flows. And we show an example service flow skeleton model on the left. Service flow skeleton shows high-level layouts of the input configuration, including which resource to use in the test and how they are connected to compose the service flow. It also reveals interactions between resources, such as the priority competition or some request handover. To create various service flow skeletons, we utilize the insight that the interactions might be vulnerable and generate some skeletons to cover all the resource interactions. We start from the seeds of the resource interactions, extend them to the entry and exit, and finally compose some complete service flows. And this is also flexible for other heuristics. After that, we transform service flow skeletons into complete configurations. This is because the skeleton is very high level and it lacks some detailed options. To do so, we first fill the connector fields to realize the service interactions specified in the skeleton. Most simply, we can set the same value for field A in resource A and field B in resource B. After that, we extend the configurations with constraint-based fuzzing to make sure it does not break any validation. So please refer to our paper for more details. After the first 2 stages, we already have an automatic configuration generator to produce end-to-end effective input configurations. But now we will build a testing oracle to check whether the system can handle the input configuration correctly. The oracle should be as accurate and reliable as possible. So in this stage, we model the accurate behaviors between in the service mesh with the control flow graph. And the actual behaviors include some low-level details, such as priority competition, default routes, which are not explicitly written in the configuration. So in the CFG, each path represents a representative request. To build the CFG automatically, we build automatic interpreters to transform the input configuration into low-level CFG. The interpreter utilizes the intrinsic 3-stage architecture of service mesh traffic management. And we build some small interpreters for each kind of resource first and try to connect the sub-CFGs by resolving priority selection and adding default routes. With the CFG, we can infer the correct behavior for each request. And building the interpreter might cost some human efforts, about 2 person weeks. but it will work automatically later. We have already built interpreters for Istio and Linkerd and also provide some APIs for other systems. After the CFG building, we are now able to create real test requests and check the system right. We conduct simultaneous execution on the CFG, and each pass in the CFG corresponds to a unique request. For example, the write pass on the left corresponds to the write request on the right. We use the SMT solvers to know which request corresponds to which pass and what it will be after the service mesh processing. We check the location and the content for each request with our test driver and compare it with the result calculated from the solver. We also check whether the system panic or raise any errors. So here is the full workflow of MeshTest. We can see that the testing is evolving from the very abstract service flow skeletons to configurations to concrete CFG and finally to real service requests. We model service mesh in different granularities to avoid the explosion in generation stages and inaccuracy in the Oracle checking stages. We have tested two most widely used service mesh systems with MeshTest. They are Istio and Linkerd. We have found 23 new bugs. 19 has been confirmed and 10 has been fixed. We believe that MeshTest also works on other commercial and academic service mesh systems, such as App Mesh and Application-Defined Network. We evaluate the testing coverage and efficiency for MeshTest. MeshTest ensures 100% coverage on the pairwise resource interactions. It increased the overall testing coverage of Istio traffic management by a lot % and significantly increases the coverage on resource interactions. The input generator creates 2,500 configurations per second, and the Oracle checks each input with 29 different requests on average. MeshTest does not need any modification on the code base, and it only needs to be updated when the specification of the service mesh changes. So finally, we are glad to show a real bug found by MeshTest. With the input configuration on the left, the request full-API returns a not found error. This bug occurs only when two resources have the same host and different rules, and the one with higher priority has a delegation rule. Existing tests did not detect it, mainly because the relationship between the resources are somehow tricky. MeshTest found this bug by generating the configurations containing the tricky interaction, creating a request hitting the rule, and detecting difference between the actual and the reference one. So to conclude, MeshTest is the first automatic end-to-end testing framework for service mesh. It is composed by an input generator and an output and the automatic testing oracle. MeshTest has found 23 new bugs till now. So thanks for your attention. So please be free to raise any questions. Thank you.